Hey physicists, this is going to cover material from day 3, week of March 16th. Many of you are out for athletic events or various other events on day 3 when we covered electrostatics and ventured into our motor lab. So I just want to cover that. Hey, so far we've looked at a couple of items. One is up until now, and that's electricity, which is the flow of electric charges. Typically, we've been describing it this way in our analytic model, is that that electric charge goes from the positive terminal or area of high potential down, does some work going through maybe a resistor or whatever other device, and then to our low potential. We've also looked at, so far, we've looked at electric charges. And we know that, let's see, like charges repel. It would be for 2 positives or for 2 negatives, and opposites, you know, plus and a minus, will attract, or a minus and a plus, they attract. Okay. These ideas of plus and minus were given to us by Benjamin Franklin, and he came with the idea of an electric fluid well before the idea of protons, neutrons, and electrons were known. He did his work in the late 1700s. It wasn't until the late 1800s, first part of the 1900s, that people really identified electrons as being the charge carrier in an electric circuit. So we actually realized what is happening in an electric circuit is not those charges going from the positive to the negative, but really it's the negative electrons are flowing from the negative side of the battery over to the positive side of the battery. Okay, why are they doing this? Remember, down at the negative side, we've got an excess of negative charges, and we know that like charges, 2 negatives will repel, so that the charges are being pushed out of the negative end of the battery. Okay, and where do they want to go? Hey, we also know that opposites attract, so that those negative charges would be attracted to the positive side of the battery. By looking at these two things, one being electricity, the movement of charges in a wire, and 2, looking at electric charges and how they will repel or attract, tells us why electric currents actually move in wires. Now, something else that's associated with the moving charges is something called a magnetic field. And please note, many of the images I am taking here are from the Learn lesson that you would have had on day 2. Okay. But we can see this here, that if I have current moving in the direction of my thumb, moving up through my thumb, it was found in the mid to early 1800s that magnetic fields came about anytime we had moving charges. You may have done this yourself when you've ended up taking a piece of wire, wrapping it around a nail, connecting it to a battery, and made a simple magnet, or in this case, an electromagnet. Let's take a look at this. If I have current that's passing from, let's see, the positive to the negative end, where again we're using the current model, we're not worried about movement of electrons, just that it's movement of charges, okay, that a magnetic field wraps around the wire. It doesn't come out from the wire, it doesn't go parallel, it doesn't go along the wire, but it actually wraps itself around the wire. What would this mean? A compass can use the Earth's magnetic field to help someone, a sailor, a pilot, determine direction on Earth. And the reason for that is that the entire Earth acts like a giant magnet. That any type of a compass, and you've probably seen them, I end up having an arrow here, you know, there's usually a north, it pivots around on some type of a pivot, the other end points south. Okay. When placed in a magnetic field of the Earth, this will swivel around on this pivot and point north. Okay. If I put it in the presence of a fairly strong magnetic field, that'll overwhelm the Earth's magnetic field, which is pretty small, and will point out the direction of the local magnetic field. Now let's take a look at the magnetic field in this drawing here. Now, so please imagine that we have a piece of paper. Now the challenge here is that we have a 3-dimensional effect and only a 2-dimensional viewing screen. But imagine I have a paper sitting flat, and through the center of that paper, passing normal or at right angles, is this wire that's carrying current. Okay. Now if I were to place my compass at various places on around the paper, what I would find is that over on this side, the north end would point over this way. Okay. Over on this side, north would actually point the other direction. Along the front, north would point this way, and along the back, a little bit tricky to see that, it would point to the left. If we were to connect these all together, we'd see, just like we have in the drawing here, is that these arrows would make complete circles around the wire. And we can determine the direction of the magnetic field by using our hands. This is actually called the right hand rule. If I end up placing my thumb in the direction of current flow, then the magnetic field wraps around the wire in the direction that my fingers are wrapped. In this case, in the right, I would use my right hand. Okay, and let's see, magnetic field. I'll use the letter B. Don't worry about that, it's just the letter B. Now I'm going to come up with the interesting condition to say, hey, instead of having a straight wire and having the magnetic field wrap around it, what if I wrap the wire in a big loop? And I'm going to do that. I'm going to just draw something here, so just bear with me for a few moments. I'll draw a battery here, plus and minus side. I'll come up here to a switch. Okay. And then I'm going to make loops of wire. So please imagine that the wire, as I draw this, goes to the back, and it comes back around closer to the front. I'm going to keep doing that several times, around and around. Again, remembering that let's see, I'll come back around to this side of the battery. Okay, that for the current here, it's traveling this way in the front. I'll try drawing that a little heavier so it's more obvious. And then in the back, it's traveling this way. Okay. So now the challenge in our head is, once I close this switch, let's say I go ahead and close that. Okay. Now I can expect current to start flowing. And so which way is the magnetic field? You're going to have to use some imagination on this one. Okay, but in the front, I'll put my thumb in the direction that current is flowing, and then I'm going to have my palm facing me, and have my fingers on the inside are pointing up. So I know the magnetic field points up on the inside. Okay. Imagine as I wrap my fingers around, pointing them back toward me, that on the outside of the coil they point down. Okay. Let's go ahead now to the other side. Now I'm going to have the back of my hand, my thumb this direction, my fingers. For this side, I'll put my knuckles here so you can see that. Okay, again, let's see. On the inside, the magnetic field is pointing up. On the outside, it's pointing down. So remember, on the inside, I have a magnetic field that points up. Okay. And on the outside, and I might put my loop around here. On the outside, I have a magnetic field that points down. I can go and connect those. And that's what my magnetic field looks like. When I have a loop of wire, is the magnetic field points up in the center. And pointing up on a magnet, probably more familiar with a bar magnet, there's a north end and a south end. And so the end that it's pointing up is called the north end of the magnet. For the Earth's magnetic field, it's the end of the magnet that would point toward Canada or toward the North Pole. So hopefully at some point in the past you've seen something that looks like this. We have a magnet with a north and south end, and the magnetic field lines that leave this coming out the north and wrapping back around to the south. What's interesting is if this is generated by a permanent magnet, which it looks like here, or generated by loops of wire from an electromagnet, they really, the magnetic field lines do not look any different. You either have our permanent magnet, just like this, or a loop of wire wrapped around and around, kind of horizontally. Again, this is a little bit difficult to see because we're trying to imagine something that's happening in 3 dimensions on a 2-dimensional surface. But again, we can think of it going back, okay, to the back, and then looping back around to the front multiple times. And so maybe once upon a time you've played with something like this. We take a battery, our source of energy, we attach our wire, one to the positive end, current flows around here, around and around and around the nail, and then back to the negative end. 2 things. One, as we wrap the wire this way, the way we've just seen that, we know it'll generate a magnetic field straight through the center. Next question is, hey, why do I end up putting a nail in there, or what's the advantage to that? The nail itself is not magnetic, although if I do bring a magnet up to it, it becomes magnetic, and that's where it has an advantage. The reason that a nail will be attracted just like we were doing work with the wall and the balloons, is it has both lots of norths and souths spread all the way through it, north and south poles of a magnet, but they're not aligned any particular way. It isn't until we provide this magnetic field that the magnets inside there say, hey, this is a preferred orientation. Once they all line up, then you almost get a magnifying effect, or you actually do, where this small bit of current and magnetism that's provided by the wire activates all the little magnets inside the nail, and the nail becomes a much stronger magnet. Now in class I made a brief demonstration similar to this, where I took a wrap of wire around a nail and then picked up several nails or paper clips. As soon as I disconnected the battery, the magnetic field around the wire disappeared, and then the paper clips fell off. In a second test, what I did is I wrapped it many more times around that nail and found out when hooked up to the battery that the magnetic field became much stronger, as evidenced by being able to pick up 2 or 3 times as many paper clips. Hey, so the final thing we went over on day 3 was to introduce our topic 3. Hey, so the other thing I asked students to do on Friday was to make a force diagram of the paper clips being picked up by the magnet. Well, can't really videotape that, but I can show you this particular item. Let's talk about that. Okay, I'm going to have, there's a large magnet. Now, the operator inside the crane can turn on and off an electric current, and then that makes the large metal slab up above magnetic or not. Down here, we have an engine block. Okay, so we're going to see what we can do with that. Think about the forces on this right now. Probably expect right now we have force of gravity down on the motor from the Earth. Right now it's sitting in the truck bed just from normal force. But let's let this run, and I want to think about what forces are acting on it as it's being lifted off of the truck bed. So right there. Okay. Think about that. It's being lifted from the ground, has going from no motion to speeding up, so we know there's an acceleration upward. We know that gravity is still acting on it, so maybe take a few moments, pause this video, and make a force diagram for it as it's being lifted off the truck bed. So go ahead and pause that. Hey, so we have the next item. Maybe it's a refrigerator being picked up. This is just the instant as the object is being lifted off the bed. So we have the force of gravity on the, I'll call it refrigerator, from the Earth down. But what's acting up? Okay, we have a new force that we're talking about, a magnetic force. So we have a force magnetic on the refrigerator from the magnet, I guess we call that, upward. And that force, because it's accelerating upward, would actually be more than the force of gravity. We find out a little bit later that that magnetism force and the electric force are actually related. You can only have you have to have one to have the other. Right now we can think of it as 2 different forces. Now the final part that we did on let's see, day 3 before starting in on the lab was a little description of the lab. And here we have a fairly simple electric motor, and all electric motors have these components. They have a magnet, because magnets, depending on if we're talking about north or south pole, can either pull or push. There's a loop of wire. Why a loop of wire? I think we found out now. If we run a wire in this type of a shape, we can create a magnetic field with a certain direction. And depending on that direction, or pull, north or south, we can either pull or push from another magnet. What else do we have here? We have the battery, our energy source, and then wires to get or these paper clips to get the energy from the battery up to our loop. And the challenge was to make this into a motor, and a motor will be something that can create motion. And so let's see how this little motor works. Okay, so I'm about to place the coil on our little conductors here, give a little bit of a push, and there it goes. We have alternating attracting and repelling forces from our magnet. And this is the basis for every electric motor.